Now let's see this state diagram. I already told you what are the states, and now let's see the relationship, which means what are the events that will trigger the transition from one state to the other state. So now if you look at the state diagram, first thing is you will be in the new state. New state means the process is not created, the process is about to be created. So new state is in the secondary memory which means here you can call that process as a program itself, right? And once it is created, it will move to the ready state. So ready means it is ready to run, that is the meaning of it. And at any time many number of processes can be in the ready. Now one thing you should decide is how many states can be in the ready at any time, right? That is a good decision, that is the actual decision you should take. The reason is, depending on the resources you have, you can get those many processes. Let us say you have 1000 processes available in the hard disk which want to run, but then the programs, right? But then you cannot run all the programs you cannot bring all of them into the main memory at the same time. Therefore, depending on your resources, you can decide about how many processes can be in the ready state at any time, right? So generally this depends on the memory. And once you are in ready state, you can schedule the process. Scheduling or dispatch means we are picking it up and then we are sending it, right? So and then run it. So scheduling it and running it is nothing but giving it to the CPU. So once the CPU takes the process, it will execute it, and if the process is completed, which means completion, then it will terminate. So the final state is termination. If everything happens smoothly, right, then this is the best thing that could happen. See this: new state, ready state, run state, and termination. Therefore minimum number of states a process can go through is actually from here to here. How much? 4. I mean at least you need to take 4 states. See, if this is the state diagram given, then the minimum state number of states which are required to go from here to here is 4. It is like this. Maybe you can compare it to a DFA where you have transitions. Then what is the smallest string that could be accepted by the DFA, right? Similarly, how many minimum number of states are required to go from ready state to termination state? Fine. And now once you are in ready state, there are various things that could happen. Okay, let's say you are in running state, which means you are given a process for running. Then first thing is, the process might contain, I told you that a process might contain 2 times. One is CPU time and other is IO time. If a process is having lot of CPU time to be performed, then it is called a CPU bound process. If it is having a lot of IO to perform, that is called IO bound process, right? There are 2 categories, CPU and IO. Now if you are in this run state, watch it. If you are in this run state and suddenly you get a IO request, which means a process is actually suddenly asking for a IO, right? Input output. Then if you ask for it, then you are going to send it to the wait or block state, which means the process should not be again scheduled immediately. Why you should be sent to a different state, why not to the ready state is, if it is asking for IO, if you again put it back in the ready state, then again what happens is you might again schedule it for running, and again it will ask for IO. Therefore unless it will not, until its entire IO is over, and until you are sure that once you get it back to the running state, it will run smoothly without asking for IO, let it be there, right? So don't get it back. It is like this. You are just making sure that a process which will come to the running state will always be ready to run. It should not ask for IO at all. If you should make that happen, then let it go and wait in some other state until it finishes its IO, and next time again when it comes to the running state, it will run only on CPU without asking for IO. So that is why we are going to have this wait state. Got it? Wait or block. Now once the IO request is over, which means it has requested for this IO and IO is completed, maybe it wants to print something once its printing is over, or maybe it wants to read something. Once that reading is over, then we can again put it back to ready, because now it can again go to the CPU and run without any disturbance, without asking for any IO. And now once you are in running state, you could again go back to the ready state because of various parameters. One parameter is priority. What does it mean is, maybe you must be having a process which is running in the CPU, and suddenly a very high important process came into the picture. Then what you should do, you should stop it and then send it back to ready, and schedule the high important process, right? That is one thing, which means priority will cause a process to get preempted. So because of this transition, this entire thing will be multi-program. Okay, is it multi-programming? Yes. The reason is there can be many processes in the ready state. That is why it is multi-programming. And now look at this transition. Because of this transition, we are stopping a process while it is running and sending it back to ready. Even if it is ready, I am not running it. I am again sending it back at to wait in the ready state, right? Because of this transition, it is called preemption. It is multitasking or multi-programming with preemption, right? And what are the other events that will cause the preemption is, one is priority and other is time quantum. So whenever you decide that I give only this particular amount of time to each one, and after that time I want to keep on changing the process, you might decide about it, right? So whenever the time quantum expires, or whenever you need more priority, or whenever you get a process with higher priority, you are again going to send it back to the ready. Therefore this transition indicates preemption. Got it? Okay, so now these are the basically, these five are the basic states which are required in almost every operating system, which means it will be in the new, ready, running, termination and wait or block. And the other one is, depending on your requirement, resources, sometimes your resources will be too scarce that you want to suspend some process for some time, right? So for that reason we are going to have one more state called as suspend wait and suspend ready. So what is the significance of this process? This state is, I told you, so whenever we have a process, some process in the main memory, and if you don't have memory for the new process, but the new process is very important that you should make a room for it, then we just push some of the processes outside to the secondary memory, then that is called as suspend ready. If the pushing is occurring from the ready state, then they will go to suspend ready. Similarly, if the pushing is occurring from the wait or block state, then they will go to the suspend wait. Either these two, suspend wait or suspend ready, these two are in the secondary memory. See, this is in the secondary memory, main memory that is not required, and wait or block is in the main memory, and these two are in secondary memory, right? And now once you decide that it has to be suspended, they will go there. And once you decide that, okay, I have the memory, I have the resources, then again you can resume, which means they will again come back. Similarly, once you decide that you should suspend it, they will be in the suspend state, and once you resume it, they will come back. And look at the relationship between these two states. Assume that you have pushed out a memory, process from main memory to secondary memory while it is doing some IO. One more thing. In order to do an IO, the process need not be in the main memory, it could be in the secondary memory also. Even when you push a process to the secondary memory, the IO which it has initiated will still continue without any interruption. Therefore, without any problem, the IO will continuously keep on happening, right? Therefore, once you are pushing from here to here a process, that will keep continuing its IO work, and once its IO is over, it is actually ready now, isn't it? That is why we move it from suspend wait to suspend ready, so that next time it will directly come to ready, isn't it? If you let this state, the process be here itself, even after finishing its IO, then once we resume it, it will come to the block or wait state. That is why we just push it here, right? And from here it can directly come to the ready state. Got it? Now if you watch it, there are three kinds of decisions we are taking. One decision is how many processes to create, and once you decide about it, you have to live with it completely. Once you create a process, you should keep it in any of these states and then throw it out. Without doing, without finishing, you should not do anything, right? Therefore, here, whenever you are creating the process, how many processes should you create it? That is a long-term decision, right? And this is taken by long-term scheduler. So first, there are three types of schedulers here. One is long-term scheduler, second is short-term scheduler, third is medium-term scheduler. So long-term scheduler makes the decisions about how many processes should be made. Once it has taken the decision is going to last for a long time. That is why it is called as long-term scheduler, right? And coming to the short-term scheduler, what it means is, now once you have a pool of process available ready for running, then we are going to pick one of them, isn't it? Then that is a short-term decision. The reason is, that decision is not going to last forever. Only for that one process it is going to be valid, and once the process completes execution or once it goes out to the wait block, it is going to be invalid, right? Therefore, what is the meaning of this short term is this decision will not last forever, and short term decision is made here, right? So short term is made by short term scheduler, and it is also called as dispatcher or short term scheduler. And second thing is, whenever your memory is full, you are going to suspend it, right? And either from here or here, right? Either you are going to suspend from here or suspend from here. That suspension decision is going to be made by medium term scheduler, because once you suspend it, it is not going to be there forever, or it is not going to be there for a small amount of time. That is why it is called medium term decision. It is called as medium term scheduler. Okay. Now we are talking about this schedulers. There are three types of schedulers: long term, short term and medium term. So we can call it as mid-term scheduler, short term and long term. So long term decisions are when to create a process, right, as I said. But then this is also called as degree of multi-programming. Degree of multi-programming is degree of multi-programming. Degree of multi-programming is number of processes that can be present in the ready state at maximum. So if you say that degree of multi-programming is 100, it means that you will have at any time 100 processes which are ready to run in your ready. That is the maximum number of processes. You cannot go beyond 100, but then it doesn't mean that you cannot have less than 100, right? So degree of multi-programming is decided by long-term processor. If it converts 100 processes to the ready state, then the degree of multi-programming becomes 100. And once they are in ready, they can just scramble themselves among all these states. That is okay. But then the main decision is taken by long-term. Now long-term processor decisions are going to have significant impact on the performance of the system. Assume that long-term scheduler has chosen all the jobs which are IO bound, which means all the jobs require to do more IO than any other work. If that is the case, then what happens is most of the time CPU will be idle, because whenever you pick a job and give it, that is always going to block state, and all the process might go to block state if all of them are IO bound. IO bound means they need lots of IO, and CPU bound means they need lots of CPU, right? Then if you choose only a CPU bound, obviously the performance or the utilization of CPU is going to be high. That is for sure. I mean, CPU is going to be busy all the time. But then what happens to the jobs that doesn't have only CPU time? I mean, if the jobs are not just CPU oriented, if they have even IO to be performed, then what happens to those jobs? They will completely get starved. Therefore, long-term scheduler should have a mix of it, proper mix of it. You should take a combination of some of them from the CPU bound and some of them from the IO bound, and you should have a mix of it, so that even if one of the process is waiting in this wait or block state, other process will be running, right? So that is how you should have a mix of it. Or long-term processor is going, like scheduler is going to affect the performance of the system a lot. And then the short-term scheduler, the short-term scheduler will pick a system from here and will give it to this, right? But actually there is some operating systems say that there is something called as dispatcher, which is they combine this with the short-term. But then you can think of it like this: short-term scheduler will decide which process to be executed next, and then after deciding it, it will call dispatcher. Now dispatcher is the one software which is responsible for moving a process from here to here, and then a new process from here to here, right? Therefore, whenever you try to change any process from the CPU, you will first call the short-term scheduler, which will choose a process to be scheduled, and then short-term scheduler will call the dispatcher. Dispatcher will do the remaining work. What is it? It will pull out one process and put the other process there. It is called as context switching. Context switching means you should replace completely the status of the CPU with the status of the new process from the old process, right? Now context switching is nothing but saving the context and then updating the context, right? Now this depends on the time taken to do this context switching depends on the size of the context. If the size of the context is too big, then everything has to be moved out and then moved in and then updated, everything has to be done, right? Therefore the size of the context has to be as minimal as possible so that the context switching time is going to be very less, right? So here the delay, here the what are the main things that will get affected is you should have a very good short-term processor, right? Short-term scheduler, so that it will pick up the process in such a way that there will be less number of context switches, because every context switch is going to take some time. That is called as context switching time. That depends on size of the context, right? So what do I mean by it is, if P1 is executing, if P1 has to be removed and P2 has to be get on, you should change this, you should remove this and then you should schedule it, right? Therefore it is going to take some time. That is called context switching time, right? And then that is all about this dispatcher and then short term scheduler. And next one is medium term. So medium term is not that important, in the sense if the resources are not available, it will just suspend and resume, right? So when the resources are available, it will resume. When the resources are not available, it will suspend, right? And it is going to impact something called as swapping. This is called swapping. Swapping is moving a process from the main memory to the secondary memory and then getting it back is called swapping. So you need a efficient medium term scheduler, so that this swapping is going to be less, because swapping is going to take considerable amount of time. You are going to send a process to the main secondary memory, and again secondary memory has to come back, right? So here you should make one decision about what kind of process has to be moved out, so that this swapping has to be as less as possible. Got it? So long term scheduler is related to performance, overall performance, and short term scheduler is related to context switching time. Therefore it also impacts the performance. And the medium term scheduler, it actually impacts the swapping time or the swapping. Therefore it too has a impact on the performance. Anyway, all these three are going to have some impact on the performance of the system. Got it?